Good morning, guys. This is Ken Cantor with Flowmaster USA. Welcome to the Gas Turbine Auxiliary Systems Fuel and Lubrication webinar. We appreciate your attendance. We have the opportunity to present to you through a customer presenting as well as Arlie Netzel presenting. So this will be a very good webinar and I think very educational from a couple different perspectives. You see the agenda, and we will walk through. We have Tom Hayek from Rolf Group International, and he'll talk about his experience using Flowmaster in some very specific applications, including lubrication. And then I will also introduce Arlie Netzel to demonstrate Flowmaster specifically, and we've got a couple, actually 3 case studies there to show how Flowmaster is utilized. We do have a question and answer period at the end. And we look forward to sharing our understanding of the tools and the industry with you, and you're sharing back your knowledge and experiences with us. At this point, I'd like to introduce Rolf Group International. Rolf Group International is an independent gas turbine engineering company. They have the ability to complete designs of entire modules such as aero, thermal, structural, and mechanical systems. The company is actually comprised of engineers and managers formerly with a major gas turbine OEM. Rolf Group International uses commercially supported state-of-the-art development tools as they work with OEMs and first-tier suppliers in the gas turbine industry. At this point, let me introduce Tom Hayek, the president of Rolf Group International.
Good morning, everyone. I just wanted to take a couple of minutes and tell you about a little bit about how we use Flowmaster and what we do with it, and what we see the major capabilities are of the program. I think one of the reasons why the Flowmaster fellows asked me to say a few words this morning is the fact that we are not only users, but we also are under contract with a supplier of gas turbine engines, or producer of gas turbine engines, and to modify and make improvements and adaptations to the program. We are about 4 months into that contractual obligation and have already made certain steps forward in some areas, especially in the area of modeling lubrication systems for a turbofan engine of about roughly 30,000 pounds of thrust. Relative to our capabilities, the company started in 2004. Most of our capabilities are in the aerodynamics areas, compressors and turbine designs, but we have branched out into other things like mechanical component designs and integration, recuperators, 3D CFD analysis, including combustion, and structural and thermal analysis, all the things you need to do to design compressors and turbines. As part of our overall capability to deliver what I would call turnkey solutions for components, we do have a requirement for flow network analysis, and that's what we use Flowmaster for, and that's what we're going to be talking about today. Some of the current projects that we're undertaking, just so you see the breadth of scope of the capability, we are doing an aerodynamic redesign of an 8-stage axial compressor for a commercial turbofan, doing a 4-stage low-pressure turbine, including the transition duct and the exhaust case. And these are complete designs, not just aerodynamics. This includes structural, thermal. Again, touching on Flowmaster, we are doing a complete lubrication system, and that's, of course, where we're using Flowmaster exclusively. When I started counting up the years of experience that we've had, we came up to 160, and I stopped because I didn't want to go any further. But as Ken mentioned, most of us are former OEM people at various levels of management or senior engineering capability. And we do have some young engineers that we recently brought on board, and they're still training with us. What I thought I would do is just show you a typical sketch, very simplified sketch of a lubrication system for a gas turbine. For most of you, I think, are in this business, so I'm not going to be telling you anything new. But this is a representative schematic of the system that we've laid out for the customer. 3 bearing compartments, 5 bearings, tower shaft, angle gearbox, accessory gearbox, supplying oil to bearings for lubrication, cooling the compartments, as well as for bearing damping. Pretty classic layout, hot oil tank design, single filter. At least now, we started with 2 filters, we're down to 1. Fan oil cooler, fuel oil cooler in the system, and a centrifugal de-oiler. It seems simple when you start looking at it, but for those of you that have done lubrication system designs, it's actually quite complex, because what you don't see here is a myriad of valves and bypass valves and check valves and all kinds of other stuff that's not on this picture. The other thing that's potentially not intuitively obvious is the fact that you've got a mixing of oil and air in all of these areas, and that complicates the modeling picture significantly. What we have done is, and I will just show you at least small portions of the model that we've built. Here's an example where we've lifted a forward compartment breather system model, modeling flow coming in through labyrinth seals into the bearing compartment itself. We've got a fixed volume compartment, and then air, significant amount of air actually, with about 10 or 15% of oil content gets passed through a de-oiler and dumped overboard. Not a simple modeling process. 2-phase flow has to be utilized here to calculate the proper pressure drops, but with a certain amount of customization, we were able to do that very successfully using the FlowMaster basic elements. Here is a simplified picture of the scavenge system, where each one of the compartments plus the accessory gearbox and a tower shaft transfer gearbox areas are being scavenged by 5 stages of a scavenge pump. Also a 2-phase flow proposition, because about the oil is being scavenged out of these compartments in somewhere 3 to 4 to 1 ratio with air, and that also has to be accounted for, so proper pressure drop calculations can be made to avoid potential cavitation on the pumps, make sure that the inlet to the pumps has adequate pressure. But again, successfully demonstrated using the FlowMaster program. And here's the last part, which is the supply side of the system, the pressure side, which basically shows you the oil tank pressure pump taking oil out, running it through a supply filter, through the 2 heat exchangers with the appropriate bypass valves. You can see the manifold from which the supply oil gets distributed to the various compartments and then gets further subdivided into each individual nozzle, or a orifice-like representation for the bearing damping system. And here the difficulties are not as pronounced relative to two-phase flow because you don't have any two-phase flow issues here, but plenty of complexity in modeling pressure losses and trying to set up the nozzle injections, the oil nozzle injectors in such a way that you get the appropriate flows at the appropriate pressure drops and the appropriate velocities coming out of the nozzles. And I will just close by saying that in this particular case, we were actually quite successful in using the fairly standard elements from the Flowmaster deck in terms of pipe elements, orifice elements, sudden constrictions, to actually model in detail the inside flow inside of a typical lubrication nozzle. And the results are actually surprisingly accurate. I was surprised when I saw how close it was to actual data. So with that, I will finish my little talk and hand it over to Ken for a sec.
Excellent.
Thank you.
Excellent. Thank you very much, Tom. That was Tom Hayek from Rolf Group International. We're privileged to have him in town in Chicago here. He's got one of his clients in for training and a couple of his people in training. So we wanted to take advantage of that and share with you his insights about gas turbine engines and lubrication and Flowmaster specifically. It's my pleasure to introduce Arlie Nutzel. Arlie is one of our application engineers with Flowmaster USA. As most of you know in the audience there, we are responsible for supporting your use of Flowmaster as you utilize it in some of your design challenges with gas turbine engines. And Arlie will show you some of the case studies that he's put together for this educational webinar. Arlie?
Thank you, Ken. Just as an aside really quickly, it looks like some of you are having some trouble either seeing or hearing the presentation. We will have a recording available after the event, in the event that you cannot see it, but it looks like it's only a very, very small number of you. So thanks. So good morning, everyone. My name is Arlie Nutzel, and I'm an applications engineer with Flowmaster USA. I'd like to thank you all for joining us for this educational web seminar, where we're going to discuss the use of 1D system simulation in gas turbine and aerospace engine auxiliary systems, specifically fuel delivery systems and lubrication systems. It looks like also a few of you do have some questions. We will have a question and answer session with both me and with Tom from Rolf Group to answer all of your questions about his presentation and about mine. So before we get to our example models, I want to highlight where system design can be of benefit to both fuel and lubrication system analysis. So let's start with some fuel system applications. In aerospace, we need to deal with issues like performance over a wide range of flow rates, pressures, and temperatures due to the changing operational requirements of an aircraft engine between idle and takeoff thrust, and widely variable environmental conditions between sea level and 40,000 plus feet. We also have issues of redundancy and failure modes to investigate. Ground and marine turbines and compressors are similar to their airborne counterparts in design, although operating conditions and environmental factors are obviously different. With ground-based gas turbines, issues of efficiency, fuel availability, and consistency, turbine reliability, and failure scenarios are all very important. There are also many automotive fuel applications that we have addressed in our automotive industry-specific webinars, which are available to view on our website. Like fuel system analysis, lubrication analysis is also an area where 1D system design software can be of benefit. Flowmaster has been used for lubrication analysis in the automotive industry for many years, and we have a robust library of specialty components to model bearings and things like rotating crankshaft drillings. In aerospace applications, reliability, efficiency, and part longevity are all critically important. A well-designed lubrication system is essential. In addition to simply modeling pressure and flow, thermal analysis is often required when modeling lubrication systems. And just as with fuel systems, ground-based and marine turbines have similar requirements to their airborne counterparts. lubrication analysis can also extend to other industries as well. Rotodynamic and reciprocating compressors used in the natural gas industry, as well as wind turbine lubrication and shipbuilding, can all take advantage of Flowmaster's lubrication model capabilities. The gas turbine industry faces numerous challenges today. First and foremost, fuel efficiency and reduction of carbon emissions are of critical importance as new designs and refinements of old designs come to market. Rapidly emerging markets and new technologies and uses for gas turbines are also increasing the demands on the industry to develop more faster. Additionally, there are the ever-present demands of government certification and competition that force the industry to streamline design processes, shorten development cycles, and reduce costs. The challenges of the industry and the application eventually filter down to engineering, which is always asked to design things faster, better, and for less cost. With simulation, we can cut down on physical testing, which can greatly reduce costs. With simulation, we can also investigate scenarios that cannot practically be tested. And with good use of simulation, we accelerate the design process and make the end product better. We can set up a prototype model before exact geometric information is needed. Later on, we might have validated models for our design. Then, when design changes are considered, we can simulate those changes before trying anything in the real system. We can run operational conditions and model system events with a transient case. And Flowmaster is a 1D fluid flow system simulation software that is designed to help engineers quickly solve their fluid flow problems to find pressures, temperatures, flow rates, and system and component level variables. Flowmaster has long been involved in modeling various systems related to gas turbine engines. This includes both stationary gas turbines and aero engines, like the one you see here. These systems include applications like fuel and lubrication oil delivery systems that we will investigate today. But there are several other ancillary air systems that are commonly modeled with Flowmaster as well. These include things like purge air and atomizing air systems. Flowmaster has an internal duct component that can be used for modeling the complex flows and heat transfer characteristics of the internal passages of rotating turbine blades. And the latest developments to Flowmaster gas turbine are centered around the modeling of the secondary airflow in and around the rotating components inside of a gas turbine. With Flowmaster, there are a number of different types of analysis that can be performed, both incompressible systems like fuel, oil, and water, or compressible fluid systems like high-speed air can be analyzed. For simple pressure drop or flow rate calculations, you can run a steady-state analysis. If you're interested in seeing what happens with time-dependent events, such as relief valve dynamics, system startup, or things like pump trip scenarios, you can run a transient analysis. We will look at both steady-state and transient examples in today's presentation. You have the ability to account for heat transfer during compressible analysis as an option. In gas turbine and aerospace engine design, we have a specialty analysis for secondary flow modeling. This analysis type has a swirl solver and a wizard for quickly building cavities with different frictional faces. In addition, our latest version adds the ability to break down the flow into radial, axial, and tangential flow velocity vectors. Finally, we have design options such as flow balancing, which is designed to help you size your system, and COM automation that allows you to link to external software like Excel and run a parametric or automated series of runs. Flowmaster also has its own built-in parametric study abilities, which can be used to optimize and automate your models. We took a look at the analysis types, but now let's talk about components. Flowmaster comes with over 200 built-in components that you use to construct your model. Flowmaster is offered in several different industry packages, including general systems, aerospace, and the one that we'll talk about today, gas turbines. The modeling done today could be done with any industry variant, however. The components used are primarily pipes for pressure loss calculations and lubrication passages, geometric-based components such as junctions, bends, and orifices, which use built-in loss data from the Internal Flow Systems Handbook by Dr. D.S. Miller, and thermal components to calculate thermal effects in the system. There are some components specific to lubrication, such as positive displacement pumps and automotive journal bearings. Also shown in the bottom row of components on this slide are some gas turbine library components, such as a rotating gas passage, a secondary air cavity, and a brush seal. Besides these built-in components, Flowmaster also provides a way to run a script to make your own custom algorithms, or even create your own component with all the capabilities of the standard Flowmaster components you see here. The interface generates a code stub as a starting point, and from there you can write your code in C# or VB.NET. We train our customers on how to build such components, or we can also do this type of work as a consulting service project. Now that you have a basic idea of Flowmaster's abilities, we can demonstrate how it's used in several case studies. For our first case study, we will investigate a simplified aero engine fuel feed system. Instead of focusing on the fluid flow aspects as we have in past webinars, we will start with a pre-built model and focus on the control systems that regulate flow and pressure. Here is the system itself. On the left-hand side, we have modeled the inlet from the fuel tank as a constant pressure boundary condition. Because this is an aircraft engine, redundancy is key, so there are two parallel flow paths. Each has its own fuel filter, modeled as a simple discrete loss, and an engine-driven positive displacement pump. Each PD pump has a pressure-regulating valve that reroutes flow back to the inlet of the pump to restrict the output pressure of the pump to a desired value. Should one of the pumps fail, a cross-feed line will allow the flow from one path to supply the other. The excess flow and pressure produced by the pump was sized to handle this overhead. Moving right, we have a flow control valve that splits into lines that feed the individual fuel injectors in the combustion section of the engine. The focus of this model is on the control systems we employ. We will discuss three main controller assemblies: flow control, pressure control, and engine speed feedback in detail. First, the flow control valve. We start with a tabular controller that supplies a programmable rate of change of desired mass flow rate. Here, you can see we start the model with a flow rate to approximate idle speed. Then, over a period of 1 second, we change our desired set point to 5 pounds per minute, simulating a move to take off power. To regulate the flow to our desired value requested by the set point controller, we use a mass flow gauge to read the current value of mass flow and feed that into the variable input of a PID controller to actuate the valve by the proper amount. You can see the data form for the PID controller here. Next, we'll look at how the pressure control system operates. Similar to the flow control system, we use a gauge to measure pump output pressure and feed that to a PID controller. Here, we keep a constant 300 psi set point, so we do not need to use the optional variable set point signal input of the controller seen here. The PID controller opens a valve that bypasses flow back to the inlet of the pump to regulate the output pressure. Our last control mechanism is our fuel pump speed control. This arrangement is used to model the geared connection between the turbine shaft and the fuel pump. This control includes a simplistic inertia model of the rotating mass of the engine. Here, instead of a PID controller, we are using a controller template in conjunction with a script. We can use this script to make certain assumptions and do certain calculations, and we assume that the speed of the engine pump is proportional to engine power, which in turn is proportional to flow rate. Although this is a gross oversimplification, it works for this example. We read the mass flow rate of fuel with a gauge, apply a proportionality constant to convert that to a pseudo torque value, and then we use a pseudo inertia term to simulate the resistance to change of speed of the system as a function of time. As flow to the engine is changed, the torque value changes, and the engine and the fuel pump accelerates or decelerates. Here, you can see a plot of flow demand, which was illustrated earlier when discussing the flow control system. After we run a simple transient analysis, we can then plot results of mass flow rate through the system. The delay between the change in set point and the change in mass flow is a consequence of the PID algorithm and our chosen coefficients that we tuned over several simulations. Next, we can add a plot of pump speed to show the additional delay between flow rate, which is our analog for engine power, and pump speed. This delay is caused by our simplified inertia model employed by the script. And lastly, we can plot pressure. We have plotted pressure to show you how the pressure control system and bypass system is able to cope with the changing pump speed and hold on to a consistent 300 psi set point. Like with the other systems, the performance of the pressure control is determined by the P, I, and D coefficients inside the controller that we supply, as well as the sizing of the bypass line and valve that again was done in earlier simulations. Now that the control system is complete and operational under idealized conditions across the operating range of the engine, we can investigate a failure scenario. Once the simulation has started and fuel is flowing at peak flow rate and the engine has spooled to peak RPM, we will fail one of the two fuel pumps to verify the other pump has enough capacity to supply the crossfeed line to the failed side of the engine. We expect that the bypass valves will automatically close based on pressure signals from the pump output gauges, and the imbalance of pressure from the good pump to the failed pump should reroute flow automatically. We also want to investigate the effect of pump failure on fuel flow to the engine, pressure in the fuel system, and engine speed if any flow rate drop does occur. After the transient analysis was run, we can generate some result plots, the first of which is shown here. This first plot of our failure scenario shows mass flow rate as a function of time in blue. And the mass flow rate stays constant until our failure event at about 20 seconds into the simulation when the upper pump in the system abruptly stops. You can see the failed pump speed drop to 0 in the chart. You can see that sudden drop in RPM causes a spike in the mass flow rate of fuel as the valves are starting to open and reroute fuel. We can also look at the bypass valve openings as a function of time, along with the cross-feed fuel flow rate in blue. You can see again at the 20-second mark, the pump stops and the flow rate jumps from the bottom side of the model to the top. And also the bypass valves close to maintain pressure. One pump is slightly higher than the other because of the pressure drop in the bypass line. Using Flowmaster, we can build a simple flow model to analyze flows, pressure drops, and pump performance. But with the addition of a control module, either within Flowmaster or in an external application like MATLAB Simulink, we are able to take a simple flow model and turn it into a system simulation, model the transient responses of controls, and gain insight into how the combined system will behave. In our second model that I want to show today, we will investigate a natural gas-fed power generation turbine fuel feed system. We've looked at similar models in previous web seminars, but we'll delve deeper into the fuel feed controls of this model. Like the last time we observed this model, our main interest is in understanding the process of switching from one fuel to another. In this example, we're switching from natural gas to syngas. Before, we looked at the basics of Flowmaster's fluid mixing capabilities, but with this model, we will go one step further and measure fluid concentration, use the result to develop a closed-loop feedback fuel control system. One of the many challenges to overcome in a fuel switching scenario is that of fuel energy density. Because syngas typically has a lower energy content by volume than natural gas, the switch from one fuel to the other must be done carefully and in a controlled manner to ensure that turbine power is not affected. To model this energy density difference, we're going to make a few simplifying assumptions for this model. At the top of the slide, we have an equation that defines our assumption of a heating value parameter. We are defining heating value as the sum of the product of each fuel's energy density and concentration, that quantity multiplied by the total mass flow rate. Although there are other important parameters, this simplification will serve for this demonstration model. We can perform this same calculation in situ in the Flowmaster model by using gauge components to measure concentration and mass flow rate, and then use a control along with a script to do the actual arithmetic. We can then plot results of heating value coming out of the controller just like any other standard Flowmaster result. Our first analysis will be of a simple swap of linear valve openings. We will close the natural gas valve while we simultaneously open the syngas valve at the same rate. Earlier in the development of this model, we sized the syngas valve larger to account for this energy density difference of the two fluids. After running a compressible transient analysis with fluid mixing enabled, we see results of our heating value parameter. It is clear that despite our attempts to equalize heating value of the two fuels through valve sizing alone, we also need to control valve rate, as we see a 20% variance in heating value during the transition from one fuel to the other. We can remedy this problem by using our heating value parameter result from the controller and using it in conjunction with a PID controller to operate the syngas feed valve for us at a controlled rate. Looking at our heating value results again after this change, you can see now that the controlled heating value variance is almost non-existent. After attaching the PID controller and entering data in a similar fashion to the controllers used in the aero engine example that we just saw, the rate of the syngas feed valve is now nonlinear, despite the natural gas valve's linear closure. After developing our controller scheme, we can now add on the rest of the manifold model that we have used in past webinars. We need to investigate whether our control scheme will still work when the compressible gaseous fuel travels through the rest of the system. Again, here are the results just after the mixing point of the uncontrolled heating value result and the PID controlled heating value result. Although the controlled value mixing results look good at the mixing point, if we look downstream at the first inlet nozzle, and let me back up and show you, this is the first inlet nozzle, you can see that there's still a variance. In this case, it's even worse, up to 40%. This variance is a result of our changing upstream mass flow rate as we add proportionally more syngas to the mix than the natural gas we take away. This higher flow rate pushes more of the pure natural gas farther downstream out of the injectors, resulting in an increase of heating value and thus power developed by the turbine. The farther down the system we look, the worse the problem gets. The second line is a result from the farthest downstream injector all the way on the right-hand side of the model. Our proposed solution to this problem is to try and move the measurement point for heating value as close to the injectors as possible. This may introduce some oscillation into the control, as there's a large delay time and compressible gas column between the actuated valve and the measurement point, but hopefully the mixture itself is more stable. After switching the heating value measurements to just before the first nozzle and rerunning the analysis, we can compare the previous results with the new results. You can see that the heating value result for the closest nozzle, nozzle 1, is drastically improved, with a variance of heating value of less than about 5%. However, because of the additional distance still to the far nozzle, the variance there is still greater than 30%. It appears that we need to possibly add individual control to each nozzle, or we could take steps to make the volume of gas between each nozzle and the mixing point exactly identical to try and eliminate this effect. Lastly, we were concerned with the potential for oscillation caused by the distance between the measurement point and the control. As you can see, there is some noise in the valve position result, but that did not have a significant effect of oscillation on the actual heating value. With this model, we were able to quickly simulate several different aspects of our fuel switching scenario. Namely, we could use the Flowmaster fluid mixing solver to simulate the mixture and change from one fuel to another quickly and easily. We could then add controllers and gauges to measure a custom result and use that result in a feedback scenario. Then, we could easily move our control measurement point from one location to another to optimize the downstream effectiveness of our feedback loop. And lastly, we were able to determine through simulation that our system will need further modification to safely and effectively switch from one fuel to another. Because this was discovered through simulation and not through actual testing or operation of the system, we potentially save money and development or system downtime. Now that you have seen two fuel system models, let's look at the other auxiliary system we have and will discuss farther today, and that is lubrication. Although this web seminar is geared specifically towards the gas turbine and aero engine industry, proper lubrication of moving parts applies to many different industries and is a critical application of simulation tools like Flowmaster. Here is a simplified system-level model of a small aero gas turbine engine. In this model, we are not modeling each and every injector flow or scavenge system as was shown in a previous webinar and also by Tom Hayek in the Rolf examples we saw earlier. Instead, this model focuses on the system level. This model encompasses a closed-loop circuit of lubricating oil and simulates the heat transfer between the different sections of the turbine, compressor, and combustion area, as well as the gearbox that delivers torque to either the accessories or a propeller. At the bottom of the model, we have a collection sump as well as an engine-driven fuel pump and several filters. Later, we will add heat exchangers near the top of the model to take into account the rejection of heat to air and to a fuel preheat system. In order to ensure that each stage of the engine receives the proper amount of flow to ensure proper operating temperature and adequate lubrication, it is necessary to balance flow throughout the system. Here, we will assume that we know what flow rates we need to each section of the engine to achieve the temperature and lubrication conditions we want. Here, we have plotted our initial orifice size guesses right on the schematic. We can then manually iterate the individual orifice sizes to achieve the desired flow rates we want, or we can have Flowmaster solve the problem for us. With our initial guess of orifice size shown in the previous slide, we have replaced the plot with the flow rates achieved in our simple steady-state simulation here. Although these may be near the flow rates we desire, we can use Flowmaster's flow balancing solver to give us exactly what we need. First, in each orifice, we enter a desired flow rate to each lubrication pathway, which again I've plotted on the schematic. Next, we change our simulation type to flow balancing and run a quick simulation. Flowmaster then solves and reports the exact flow rates we sized for. Here we have plotted results of selected diameter, or the diameter that Flowmaster found that achieved our requested flow rate. It is then a simple process to copy and paste these result values back to the orifices in their actual diameter data fields and rerun a simulation. We have a simple-to-use macro that can also automate this process in every orifice in your model all at once. With our oil distribution and flow rates optimized, we can then start to look at the heat transfer interactions between the lubrication system and the oil-air heat exchanger, as well as the interaction with the fuel system model we created for the first case study. We begin by modifying our oil distribution system with the addition of heat loads for each section of the turbine. We add controllers along with a simple script to vary the heat added to the oil as a function of engine power. We also modeled each simple heat load component with a custom composite component to be able to model heat capacity of the thermal mass of the engine and an optional amount of convective and radiation heat transfer between the engine and the environment inside of the engine nacelle. On the right and top of the model, we add an air-oil heat exchanger to reject most of the heat from the engine. And also off the edge of the screen, we add a fuel oil heat exchanger that both cools the oil and preheats the fuel to a desired temperature. We use a temperature regulation valve configured like the pressure and flow regulating valves seen in the fuel model to maintain our desired fuel and oil temperature. Back at the system level view of our fuel system model, you can see the addition of a fuel oil heat exchanger near the fuel tank connection. All that's left to do now is connect this model with the lubrication system model. And here is the completed model with both systems connected and ready to run. Before we run an analysis and look at results, I do want to quickly show you how we're modeling the heat load of the engine and also its heat capacity. Each individual heat load component is what is known as a composite component in Flowmaster, which is a condensed collection of individual components that behave as one. We created this particular composite component for one of our earlier webinars, but I will briefly show you how they work. Here's a quick look inside of our custom component, which we previously used in our last aerospace webinar. The component is made from a subset of normal Flowmaster components that have been combined into what we call a composite. By looking inside the model, we can see how we define the various aspects of our simplified heat transfer model. A constant temperature source allows us to model the ambient air temperature in the nacelle. The heat flow source models the heat duty directly generated by the engine. And then to model the convective transfer of heat between the mass of the engine and the ambient surroundings of the nacelle, we use a two-arm convection component. Likewise, we use a radiation component to model the radiation heat transfer from the engine to the ambient environment. In a transient analysis, the thermal capacity of our model is important, so we use a point mass component to account for the thermal inertia of the system. Lastly, we use a thermal bridge component to allow us to model the heat transfer between the solid network and our liquid lubrication circuit. This includes a lumped parameter for conduction from the engine parts to the oil system. Composite components are completely customizable. Here we have designed a custom data form for our composite component with just the input data we want the user to see. Everything else is hidden and predefined. As you can see, certain properties like surface area are used by multiple parts of the composite component. We can share one data field with many individual components within the composite at once so that duplicate entries are not needed and data entry is simplified for the user. Now that the composite is created and in place in the model, we need to calculate how much heat each portion of the engine is rejecting to the lubricating oil. Again, we make a simplifying assumption for this demonstration model and assume that the heat flow rate is proportional to engine power, which we earlier assumed was in turn proportional to fuel flow. Again, we use a simple script to perform the calculation and apply the result to our heat transfer component. Here are the results of a series of analyses performed at 10% increments of power. Here we're looking only at the heat added to the lubrication system by our customized composite component. The linear response is a result of our simple proportionality assumption, and the difference in heat flow rate from section to section is a result of different heat flow constants that we applied to each section. Here is a series of plots of oil temperature at the return of the sump as a function of engine power. The rapid rise and gradual fall at the beginning of the analysis is an artifact of the heat capacity built into our model and the difference between our initial temperature guess of oil, fuel, and solid engine mass and the pseudo-steady state temperature that we achieve at each power setting. What we're most interested in is this final temperature that the model settles on the right-hand side of the plot. As you can see, the oil temperature varies between about 110 Fahrenheit at idle and 180 degrees Fahrenheit at full power. Next, we plot the same for the fuel temperature, leaving the fuel-oil heat exchanger on its way to the injector nozzles in the combustion cans. Here the temperature varies between 80 degrees Fahrenheit at idle and 96 degrees Fahrenheit at full power. Using these results, we could refine a control mechanism to more tightly control the preheated fuel temperature or the oil temperature, or both, depending on conditions. We already saw results of generated heat as a function of engine power setting on an earlier slide, and here are the results of rejected heat for both the fuel and the air heat exchangers as a function of power. As you can see, with our current arrangement, the oil-to-air heat exchanger is sized to be considerably more effective than the fuel-oil heat exchanger. This is because there's relatively little fuel flow available to cool the oil, and there's also an upper limit to how hot we can allow the fuel to get. By the end of the simulation, the dissipated heat value exactly equals the heat rejected to the oil seen on the earlier slide, indicating that our system is indeed in thermal equilibrium. With this model, we first flow balanced the amount of lubricating oil to each part of the engine in order to achieve sufficient lubrication and temperature control. For a more thorough analysis, we could use our temperature results to update our desired flow rates to each part of the engine to optimize based on required temperature and flow instead of some fixed flow parameter. We could also model a change in design where instead of a fixed orifice, we could use controlled valves to route oil where and when it's needed to different parts of the engine. In the second half of the case study, we looked at thermal interaction between the lubrication and the fuel system. Using this combined model, we were able to quickly find pseudo-steady-state temperature results at different power settings. From here, we could use the results to further refine our system with active control to obtain a specific fuel or oil temperature for maximum efficiency or other engineering constraints. So thanks everybody for attending, and another thanks to Tom again from Rolf Group for sharing what he had presented today. So thanks everybody, and if you have any additional questions, feel free to email them to us. The information is again on our website. Thanks.